Hello, hello. We have day 2 of Unit 10 on the intermolecular forces. So on the last video, we talked about the dipole-dipole, which interacts between two polar molecules. We talked about the ion dipole force, which interacts between something charged and something polar. And then we talked about the London dispersion force, which is the only attractive force available for things that are nonpolar, where we said even if things aren't polar, for brief moments, instances, they have moving electrons that can draw them together. So go back if you don't know what I'm talking about and watch that first video. Now, the last of the types is the hydrogen bond, and by far it's the most important. It is technically a dipole-dipole interaction. So again, dipole-dipole means two polar things, but this one is special. And what's special about it is it takes a very select pairing of two polar things. But if you have this special pairing, then the strength of the interaction is much stronger than your standard dipole-dipole. And so we call it a hydrogen bond. Again, we usually don't even use the word bond for dipole-dipole and London dispersion. We call them forces. But since this one is so much stronger, we call it a bond, sort of like a covalent bond, even though it's not nearly as strong, but it's still stronger than the rest. So the main requirement is you have to have a hydrogen, hence the hydrogen bond, but it has to be bonded to either nitrogen, oxygen, or fluorine. These are notably the most three electronegative elements. And so if you have these three NOF bonded to hydrogen, then what it does is it pulls electron density away from the strongest, so that this hydrogen has the strongest possible partial positive charge that it could possibly have. So that's how on one side. Then the other component, if you see these three red dots, that is showing a hydrogen bond. On the other side, you need another polar nitrogen, oxygen, or fluorine. So this is just bonded to something else that's not itself. It just needs to be a polar bond. So if that has the strong partial negative and the hydrogen has a strong partial positive, this interaction is very strong, and we call it the hydrogen bond. Again, NOF, never order fish is how I remember, or all three of them are right next to each other, but they're the three most electronegative atoms, so they create the most polarized bonds to generate this hydrogen bond. So here's a couple examples. Here's water hydrogen bonded to itself. So here in this left molecule, oxygen has the partial negative, and then the three dots is the hydrogen bond to the hydrogen on the other. So again, this is the partial positive, and the oxygen's the partial negative. So water formed hydrogen bonds and that's what holds it together. Ammonia, NH3. So this nitrogen has a partial negative charge. It's more electronegative than the other three hydrogens. And then on the other ammonia, one of the hydrogens has electron density pulled away from it. So partial positive, partial negative, opposites attract. So you could you could orient these a number of different ways, but it's always going to be a hydrogen with three red dots to either nitrogen, oxygen, or fluorine, and specifically to their one of the non-bonding pairs. So these two show that within water and ammonia, you have hydrogen bonding, but it could also be a mixture. So you can pour water and ammonia together, and you'll get this hydrogen bonding. So on the right, you have the hydrogen that has a partial positive charge. On the left, there's the nitrogen with a partial negative. So different. Or you could flip them. On the left here, we have oxygen with the partial negative and hydrogen with the partial positive. So the hydrogen will always be the partial positive, and NO or F will be the partial negative. But again, they could be identical, they could be opposite. It just has to have some combination of hydrogen in one of these three, and then able to form with another molecule. There are some molecules that they can form hydrogen bonds with others, but not themselves. So if you look at hydrogen cyanide down here, it's forming hydrogen bonds to HF, but it could also form hydrogen bonds to water or NH3 because it's got a polar nitrogen. But if we were to get rid of the HF and say, could it hydrogen bond to itself? The answer is no. It does have a hydrogen, but bonded to the carbon, this is not a polar bond. So it's not enough to just have hydrogen. It has to be hydrogen on one of these three elements. So again, this thing can make hydrogen bonds to other molecules, but not itself. Now, this is the secret of water. Why water has an uncharacteristically high boiling temperature of 100 degrees. Again, that number probably doesn't sound, super crazy because you've always known it. But if you compare it to other things of a similar size, it is very, very large. So if you change the oxygen out for sulfur, it has the same geometry, but sulfur is less electronegative. It's not nearly as polar, and so it only has regular dipole-dipole forces. So notice the boiling point drops 160 degrees. If you change H2S to methane, where it's completely nonpolar, then with London dispersion forces, it drops another 100. So all of these have similar masses, similar numbers of electrons, but it's the hydrogen bonding, and you can even see up here, each water can make four. So there's it can form this vast network of hydrogen bonding, which is what holds it so strongly together. So again, here's those three. Those are the three you need to look out for. I know you've been needing to see some more graphs, so here you go. Here is hydrogen bonded um, to a whole bunch of nonmetals. So in red, it's the oxygen family. So below oxygen, you have sulfur, selenium, and tellurium. And then 5 is the nitrogen family, where it has hydrogen bonded to phosphorus and arsenic and antimony. 7A is the halogens, the blues, HI, HBr, HCl. 4A is the carbon family, tin, germanium, silicon. So essentially what you're seeing here, um, on the x-axis, as you go to the right, you're going down the periodic table. And on the y-axis, it's boiling point. So the things further down on the periodic table have higher boiling points than the things further up. And that's mostly just due to size. So as without hydrogen bonding coming into play, as the molar mass goes down, there's less electrons, it's less polarizable, and the boiling point goes down. And if we look at 4A in the carbon family, it continues on. So from silicon to carbon, the boiling point keeps dropping. They're still all non-polar, but what really sticks out is when you then look at nitrogen, oxygen, and fluorine. So notice how these three, they drastically jump up the boiling points. So as soon as hydrogen bonds are able to be formed, the boiling point is significantly increased because their attraction towards each other is much, much stronger than all of the other forces that we are seeing over here. So anytime a hydrogen bond comes up, we need to make note of it. Again, in biology last year, I know you talked about hydrogen bonds. It plays a huge role in DNA and protein structure. So if you want to draw out you could draw out a protein, the amino acids linking together, or the base pair for DNA, and it's all covalently bonded that makes the molecule. But but those large molecules coil and branch, and they stick together. And what makes that happen is hydrogen bonding. So here's the double helix. And on the inside, you have things like adenine and cytosine, but on the other strand, you have thymine and guanine. So here's two separate strands. And in the middle, what's holding them together, almost like a zipper, is hydrogen bonds. So much so that when you're you have enzymes like helicase that if it needs to make copies of your DNA for either replication or translation, transcription, it doesn't just pull the strands apart all at once. It comes down like a zipper and breaks single nucleotide base pairs of hydrogen bonds, one to the next, to the next, to the next. Um, but it's just these intermolecular forces in huge numbers between the molecules that hold them together. It's the same thing in proteins. It's all covalently bonded that holds the new the amino acids together, but notice how it bends and twirls. Those are folds that are held together by hydrogen bonds. So if you looked in between the atoms, there's a whole bunch of hydrogen bonds from the amino acids that keep its structure. And if it doesn't have that, that's actually one of the ways you denature a protein and make it not work, is you look for something that can disrupt hydrogen bonds, because if they unfold, then they typically don't work. Well, here all of these answers are just popping up, so let's talk through them. Which of these could form hydrogen bonds? So again, to be able to say if it's a pure substance, can it form a hydrogen bond? It needs to have a hydrogen attached to either nitrogen, oxygen, or fluorine, and yep, it's got that. And then it also has to have a polar nitrogen. So imagine another molecule of this, and yes, this nitrogen is polar. So a hydrogen on one could go to a nitrogen on another. So yes, this thing can form hydrogen bonds. Acetone is very polar. It's got electrons being pulled toward this oxygen. And so it's polar, but the only hydrogens it has are on carbon. So if they're not on the oxygen, it is not hydrogen bonding. So no, this would just be dipole-dipole. And so if you know anything about acetone, it evaporates very quickly. So it's a liquid, but if you pour it out, it will dry in just a matter of seconds, maybe minutes, but significantly faster than water. Hydrogen cyanide. So again, it's got a polar nitrogen, but it does not have a hydrogen that is attached to one of the three. And so it is not going to form hydrogen bonds. Here's urea, and yep, this one can form a ton of different hydrogen bonds because it's got four hydrogens on nitrogens that could then go to this oxygen. So a lot of hydrogen bonding. Now, a different question. Since water is a really, really common solvent, we often want to know, how do these things interact with water? So could it form hydrogen bonds with H2O? So remember, water being polar and already having an oxygen, it already can provide a hydrogen attached to the oxygen. So the other component doesn't necessarily have to have a hydrogen. It just needs to also have a polar nitrogen, oxygen, or fluorine. And so if you look at acetone, it's got carbon, but we just said, nope, it can't hydrogen bond with itself. However, because of this polar oxygen, it can form a hydrogen bond with water, which is why acetone and water mix very well together. Propane, on the other hand, it does not have nitrogen, oxygen, or fluorine, so it's automatically a big no. It's not even polar, so it wouldn't even be dipole-dipole. Same thing with methane. It's just smaller. But methanol, yes, this thing can form hydrogen bonds because it's got a polar oxygen. Methanol can form hydrogen bonds even by itself, and certainly with water. Same with formic acid. So really there's three different points. This oxygen, that oxygen, and this one on the hydrogen. All three of those spots could form hydrogen bonds with water, but not this little hydrogen here because it's on a carbon. And BH3, that's also another no, because it does not have nitrogen, oxygen, or fluorine. And so here are some of the answers if you weren't listening or you just want to read it. Yep. Now, there's a term I want you to be familiar with that you've probably already heard, van der Waals forces. Now, in biology and biochemistry, some of these forces are so much weaker than the hydrogen bond that they go ahead and just lump them all together. So the weakest of the intermolecular forces, dipole-dipole, dipole-induced dipole, London dispersion force, collectively referred to van der Waals forces. And so specifically, we're omitting hydrogen bonds and anything with ions. So if it has electrostatic charges, then they're significantly stronger. And so, again, what all of these have in common is they have to be really, really, really close. Again, here's the van der Waals contact distance point. As they get closer and closer and closer together, then we find that the attraction gets stronger. This is actually the magic of how tape works. When you press it onto a material, it forms just billions and billions of close contact points that form all these different types of weak intermolecular forces. But again, when you start grouping them together in the masses, it can add up. Here's a fun video that talks about how tape works. Oh, that's going to cover it up. I can't make that go away or even move it. But what is stronger, glue or tape? So they work in two completely different ways. Glue, instead of the van der Waal force, it kind of just makes a connecting bridge that just kind of grabs on, fills in crevices. But yeah, you could watch that video. But tape and the van der Waal force. I usually like to talk about the geckos here. They have this really cool feature where they can cling to pretty much any flat surface where we would normally struggle to do that. And the secret behind that is if you zoom in with a microscope, you'll find on their hands they have this vast forest of what are called spatulae, and these spatulae, as kind of shown in this little image, they put their hand down, and when they pull their hand down, these little protruding particles lay down and form just a huge number of contact points that build up these van der Waal forces. And so for just one hand of a gecko, it can hold 10 times its own weight. And what's neat is they're kind of like smart adhesives, because as soon as they stop pulling down, and these little tree-like projection things stand up with less contact, it then is no longer sticky. There's a couple videos at the bottom that we would watch if we were together. I hope that you want to watch them. There's some neat technology where people are making adhesives that are we've now currently had people been able to climb whole buildings using this type of synthetic carbon nanotubes to do this. So I want to give you a brief idea concept of like the relative strength. You don't have to know these numbers, but in the last chapter we talked about covalent and ionic bonds. And again, notice in terms of these would be the energies needed to break: 300 to 400 kilojoules, 600 to the 1,000 kilojoules for both covalent and ionic. So again, those intramolecular interactions are very strong. Now, below this dotted line, here's our new one. So the hydrogen bond, again, it can get up to as strong as 40 kilojoules. So that can still be about 10 times weaker than the covalent. But if you compare it to dipole-dipole, then that's only between 2 and 10. And London dispersion, when things are nonpolar, that's like less than 1. So when you have, I want you to know, hydrogen bonding stronger than dipole-dipole, which is stronger than London dispersion. And we tell which one's which by whether it's nonpolar, polar, or polar and happens to have hydrogen bonded to never order fish, or nitrogen, oxygen, or fluorine. So on the homework, there's a few questions that are going to say, hey, I want you to put these and rank them by their relative boiling points. So the thing is, the stronger the interaction, the higher we would expect the boiling point. Because to boil them, you have to break these intermolecular forces. So the number one question you have to ask yourself, is it polar? So, is it polar is something we talked about in the last chapter that you took a test on. And so you have to consider differences in electronegativity. You have to consider bond symmetry and whether dipole moments cancel out. I'll try not to be extra tricky on that, but you do need to be able to look at something and generally say, yep, that's polar, or no, it is not. So if it's not polar, then the answer is pretty easy. Okay, it is a London dispersion force. So if you look at gasoline, gasoline is a liquid, um, a very volatile liquid. If you ever accidentally get gasoline on the concrete, it'll evaporate with it within a minute. But it's non-polar. It's made up of a bunch of just hydrocarbons with no oxygen, no nitrogen, nothing to make it polar. But it is just London dispersion force. It has only instantaneous dipole moments. Now, if it is polar, well, then you have another question to ask because it could be either hydrogen bonding or it could be dipole-dipole. So the way we distinguish is we ask, does it have hydrogen bonded to one of these three special magical elements? Because if the answer is yes, oh good, it's hydrogen bonding. If it's no, if it's polar, but it's just, weak polar, then it's dipole-dipole. Now, if they're nonpolar, we can still differentiate things that are nonpolar. Oh, sorry. So hydrogen bonding highest, second highest, and then nonpolar things with LDS are going to be the lowest. But we can then still compare other nonpolar stuff by looking at how big is it. So remember, the more electrons there are, the larger the mass, the more polarizable it is. And the bigger that is, the higher the boiling point. The lower that is, the lower the boiling point. So to finish up today, let's practice. So we want to state what are the intermolecular forces, and then what we're going to put them, assuming they have similar mass, then what would be the order of increasing boiling points based on the different types. So we look at carbon, we notice, or methane, it's very symmetric. There are no polar bonds, so it's nonpolar. So just by saying nonpolar, we automatically know this is a London dispersion force. Here we have formic acid. We have two oxygens that generate polar bonds. This thing's not symmetric, and so this thing is polar. So it could either be dipole-dipole or hydrogen bonding. Now, by pointing out that, oh, it's got a hydrogen on one of those three elements, we can then say this is hydrogen bonding. Here's propane. Similar to methane, nothing special. There's no polar bonds. It is going to be non-polar. And so then London dispersion force. And then finally, hydrogen sulfide. This is what you find in rotten egg smell that gets produced as a lot of things decompose. Fun fact. So sulfur is more electronegative than hydrogen, and because it's bent, the dipole moments don't cancel, and this thing is polar. So again, either hydrogen bonding or dipole-dipole. But does it have hydrogen on either nitrogen, oxygen, or fluorine? And to that we say no. So this thing is just dipole-dipole. So we got London dispersion, hydrogen bonding, London dispersion, dipole-dipole. So then, knowing these different types, we can rank their relative boiling point based on what intermolecular force. So the highest is always going to be the one with hydrogen bonding. So formic acid will have a higher um, boiling point than the rest of these three. And then after that, it'll be, well, what else is still polar and just dipole-dipole? And there's hydrogen sulfide. The lowest, will be the things that are London dispersion force. But what we said we can do is we can compare the number of electrons. And so you can easily look at this one and say it's bigger. So it will have a higher boiling point, propane over methane. With more electrons, it's more polarizable. There's more electrons that can be shifted to one half or another temporarily to make this thing condense. Oh, I went too far. So methane then is the lowest. Finally, draw a water molecule of hydrogen bonding to HCN. And I already have that in here, so I'm going to just go back, 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 back. Here it is. Well, okay, that's not water, but replace this fluorine with oxygen and hydrogen, and There it is. So a hydrogen on either NO or F can go to this nitrogen, but I want you to know nothing, there won't be any hydrogen bonding with that hydrogen. Okay, so there you go. So the homework that is due Tuesday by the end of the day includes questions about, again, ion dipole force, which this is the only one that has to be a mixture because it has to be something polar and then something ionic. And then we have dipole. Again, be sure you can do all these, answer these fun questions. And there you go. On Thursday, on Thursday we'll start talking about the fluid properties, or that might be Tuesday. I'm not sure. Fluid properties, and then eventually we'll move on to solids. But have a fantastic